All right, so now it's time to take everything that we've been working on with the trig functions, everything we've been working on with what the values of the trig functions are, what are the trigonometric ratios, how do we go through and we establish identities. It's time to use all of that now to go through and solve trig equations. So let's start off. In this particular case, we're going to go through and write a recursive formula for the solutions to the equation sine x is equal to 1/2. All right, so we got a couple things to talk about here. So, of course, we're going to need to deal with sine x equaling 1/2. And we need to determine where sine x is 1/2. Now, we know from inverse that sine x equaling 1/2, if I was just doing the inverse sine, that I would get a value, or I would get an angle that is in the first quadrant. However, we're trying to write a recursive formula. Recursive formula just means write a formula so that as I change to the next cycle, that this works for every single value that could happen. So before we get there, let's go through and just draw what a sine function looks like. So we know sine starts at the at the midline, comes up, hits its high point, crosses again, hits its low point, comes back up. And then, of course, it would continue infinitely in both directions. So this would continue. So if 1/2 is right here, then what I am looking for is, in my recursive formula, I want every single value where sine is equal to 1/2. So that means I have the front half of the curve, which then repeats itself here, and I've got the back half of the curve, which would then repeat itself over here. So the recursive formula is going to give it so that I have one equation, or one formula, and that will give me every single one, depending upon how many cycles I've gone through. So remember, though, with all this, that the period for sine is equal to 2 pi. All right, so that's just a couple things to remember. Now let's go through and go back to this problem here. When is sine of x 1/2? All right, so in the first quadrant, 1/2, and I can go through and I can draw. You may or may not want to do this, but it's entirely up to you. So sine is opposite over the hypotenuse. When dealing with one of the values being 1/2, the other one is square root of 3 over 2. And we know this from all the work that we've done so far. So that means that this side is 1/2. This is 1. Here's my square root of 3 divided by 2. All right, so at what angle does that happen in this quadrant? So that angle is going to be pi divided by 6. So far I know that x is equal to pi divided by 6. Or, now I have to think about, all right, so where else is sine positive? Well, remember, cosine's positive there. All are positive there. Sine is positive here, and tangent is positive here. So as I rotate my way around, and it also is just reinforced by what we see with this. So the first value that we just came up with, the pi divided by 6, is right here on the x-axis. So now we're in quadrant 2, and I have the same reference triangle drawn, which means that this angle in here, again, the reference angle, is pi divided by 6. Well, remember that over here, going 180 degrees, that's the same as pi, which in sixths would be 6 pi over 6, which means, I'm just going to grab a different color so I won't lose you. So then this rotation from here to here is 5 pi over 6. So there are my two choices in one cycle. So there is one cycle. I have it here at pi over 6, here at 5 pi over 6, and then it does not happen down here because, of course, we got negative values, and then it would start repeating itself over and over again. So how do we write this recursive formula? So we're going to give it a, we're going to give it a variable, and we're going to call it k, where k represents the number of cycles that we've gone through. So then if I go back to my colors here, and I go back here, x is equal to pi divided by 6 plus, well, it'll repeat itself again out here at 2 pi past where I was. So then that would be the first cycle away from where I started. So this would be plus 2k pi. That's the first recursive formula. The second recursive formula is now for 5 pi over 6. So 5 pi over 6 plus, since the period is 2 pi, 2k pi. So if I wanted to find out what is the next value that's associated with the front half of the curve, I add 2 pi, and that'll bring me here. If I want to know the next one, I add 2 pi, that'll bring me out here. And I can keep doing that over and over again. That's what we mean by a recursive formula. So these two formulas would represent every single value that you could have where sine is 1/2. K can be any integer. So meaning I can move positive direction or I could move in a negative direction. And it will give me every single value. All right, so let's try another example. Here we're going to write a recursive formula for tangent. So I'm going to keep blue. So I've got tangent of x is equal to negative square root of 3 divided by 3. All right, so if we go through and deal with this, I'm going to just go ahead and graph the tangent function. Remember, we've got the asymptote lines first. Grab a different color here. It looks like a cubic function that is bound by the two asymptotes, where this one is at pi divided by 2, this one at negative pi divided by 2, that's a pi. Negative square root of 3 over 3. Well, if it was just plain old square root of 3 over 3, I'd be over here, and I'd be at pi over 6. And again, I know this because I've got my table, I've got my unit circle, I have these values committed to my memory because I've done them so many times. But if you have your tables, you can figure out where to go with this, okay? So then that means that for here, when am I negative square root of 3 over 3? That's when I am back here. So I am at a negative. So x is equal to negative pi divided by 6, and then plus my recursive formula, or I mean plus the part that repeats itself. Now this is different than sine and cosine. The reason it's different than sine and cosine is because of the fact that my period, remember, is only pi from here to here. So that changes that I don't have to say plus 2k pi, I just have to say plus k pi. I don't have to worry about the front half of a curve or the back half of the curve because this just keeps repeating itself over and over again. So when you deal with tangent, you're just going to have one recursive formula as opposed to two. Now, writing like this every single time would get rather cumbersome, get slightly annoying. So what we need to do is now modify so that I'm looking at it instead of solving it with a recursive formula. I just go through and I solve it over an interval. So here, all right, so now instead I have sine 3 theta equals negative 1. All right, I like to draw my curves just so it gives me a better idea of where I am. All right, so when is sine negative 1? Let's see, so sine would be negative 1 here when I'm at negative 1 on the y. So I'm looking my way back. This is at 3 pi over 2. So that means the sine of this angle is equal to negative 1. And when does that happen? Well, that happens, excuse me, when it's 3 pi divided by 2. So 3 theta equals 3 pi divided by 2. I still got to worry about that recursive formula. So plus 2k pi. I need the interval to be between 0 and 2 pi. But the problem is, in the last example, I just had x. Here I have 3x. So what I need to do is I need to multiply both sides by 1/3, which is the same as dividing by 3. But I'm multiplying by 1/3 because I have a fraction here already. So now I get theta is equal to, okay, so 3 pi divided by 2 times 1/3. That's going to be pi divided by 2 plus 2/3 k pi. That would be the recursive formula. But what I now need to do is I need to figure out all the values that will happen in this interval. So I know my first one is going to be pi divided by 2. And then if I look here, that means that for the next one, I've got to take pi divided by 2 plus, and I'm actually going to just deal with 2 pi over 3. So 2 pi over 3 when k is 1. All right, so I got to get common denominators. So 3 pi divided by 6 plus 4 pi divided by 6, which would equal 7 pi divided by 6. So there's my next one. So theta is equal to 1/2 when k is 1. If I let when k is 0, it's 1/2. When k is now 1, I have to add 2 pi over 3. So that gives me 7 pi over 6. And now I have to again add another 2 pi over 3 until I get outside the window of 2 pi. So if I add 4 pi over 6 to 7 pi over 6, I get 11 pi divided by 6. That's still within 2 pi, because remember 2 pi would be 12 pi over 6. If I decide to add 4 pi over 6 again, I'm at 15 pi over 6. But the problem is that is outside this window. So I don't have to worry about that. So then for this equation, the only values of theta that will make this equation true are at pi over 2, 7 pi over 6, and 11 pi over 6. So the difference with what we did before is, before I just had sine of x is equal to some value, and I figured out what those were, wrote the recursive formula, and then that was all I had to do. But here, since I have a 3 theta, I still need to figure out what the angle is. So the whole idea is to find the angle, okay? And then once I found that angle, I have to deal with the fact that I now have to deal with the recursive formula, and then I need to find all the values that still land within this window and within that window only. All right, another example. This one's a little ugly, okay? So if I look at this, so then cosine of theta divided by 3 minus pi over 4 is equal to 1/2. All right, so let's deal with cosine. I just want to get an idea of what cosine looks like. We know we start at its high point, come down, around, and back up. And I want to know, when am I at 1/2? So let me choose a different color just to make life a little easier for visuals. So when we come through, I know I have, again, whoops, that should be straight. So this is quadrant 1. That's where they're all positive. Cosine's positive down here, sine, tangent. So I need when the side here is 1/2. And that happens in both of these quadrants. So then, again, knowing my tables, knowing my values, I know that the reference angle is going to equal pi divided by 3. So that means I have pi divided by 3. And then my other angle, so if I'm in this quadrant, I'm at pi over 3. If I'm at this quadrant, I'm at negative pi over 3. But notice how it's asking for the interval between 0 and 2 pi. Then I don't want to use negative, because then the problem will be I'm not in that interval. So then I now have very not pleasant looking, which is okay. It just means I have more work to do. That's not a big deal. Is equal to, so this stuff, cosine of this angle is equal to 1/2. Well, that happens in the first quadrant at pi over 3, and then plus 2k pi. Then I'm going to do this again. And in this case, it's at, well, let's see, it's at pi over 3. I'm short of going all the way around. So then that means this angle here is 5 pi over 3 plus 2k pi. So that's my recursive formula. But the problem is I still have work to do. I've got this to deal with. So I'm going to erase the stuff that I have there over here, just because I'm going to need that space. So when I erase all this, it'll give me some space, hopefully. What's left to do is I now need to go through and figure out, the arithmetic so that I can figure out what exactly is theta, because that's what I'm looking for. I'm not looking for what theta divided by 3 minus pi over 4 is. I'm looking to find out what theta is. It's unfortunate that to do this, I have to literally erase. I wish I could just create a box and then erase everything that's inside, but that's not the way this program goes. So note to self, when you create your own program, do that. All right, so now I need to solve this. So I've got to add pi over 4 to both sides. So I'm going to do a little arithmetic over here on the side, right? I've got pi divided by 3 plus pi divided by 4. And I need common denominators. So that's going to be 12. So I get 4 pi divided by 12 plus 3 pi divided by 12 is going to equal 7 pi divided by 12. Because what I did is I added pi over 4 to both sides. All right, so now I have theta divided by 3 is equal to 7 pi divided by 12 plus 2k pi. The reason I don't add it to the k pi is because I have the variable k. Now I have to multiply both sides by 3 so that I can get theta by itself. So now I get theta is equal to, if I multiply this by 3, it's going to simplify my fraction. All right, so I multiply by 3. That would give me 21 pi over 12, but I can simplify that, and that gives me 7 pi divided by 4, plus, now I have to multiply this by 3, 6k pi. All right, that's just where I end up. All right, so I come back down to this one. And again, the process is the same. I'm going to have to add pi divided by 4 to both sides. So I'm going to come back up to the top again and just do my arithmetic. So I'm going to end up with 5 pi divided by 3 plus pi divided by 4. I need to put this into 12ths. So that's 20 pi divided by 12 plus 3 pi divided by 12, which gives me 23 pi divided by 12. So now I have theta divided by 3. Sorry, it's not an equal sign, it's just an arrow. So now I have theta divided by 3 is equal to 23 pi divided by 12 plus 2k pi. And then I need to multiply both sides by 3, so I get theta is equal to, if I multiply by 3 here, I'm going to get 23 pi divided by 4 plus 6k pi. Again, it's not really the trig that's going to catch you. It's the work with the fractions. It's that's really going to catch you. So you got to be careful. All right, so now I'm going to use a different color because I'm getting way too many different colors here. So now theta, if I let k be 0, I'm at 7 pi over 4. 7 pi over 4 is within the interval from 0 to 2 pi. So that means theta equals 7 pi divided by 4. If k is 1, I'm going to add 6 pi. This is in the interval. If I add 6 pi, it's going to be outside the interval. So that means I only get 7 pi over 4 out of this. That's all I get. When I come down here, 23 pi divided by 4, that's already outside the interval. So since it's outside the interval, I don't even worry about that one. So I did all that work, not for nothing, but to show that I don't need any of it from here. So the only value that works to solve this for theta is this, 7 pi divided by 4. All right, so again, my name is Robert Main. I hope that this was helpful. This is only the first of 3 videos for solving trig equations. This is probably the longest. Hopefully this was helpful, useful, and hope you have a great rest of your day. Thank you.